So in this video I'm going to go through Unit 2 Waves and Light, ISP, Task 3, which is going to go through the start of waves. So we talked a bit about light and now we're getting really into waves. So the ideas that we're going to cover are the types of waves, describing the key features of waves, and describing standing waves and progressive waves. They're the ideas that we're going to talk about. For those of you that want to do a bit of extra research, we're looking at how electrons behave as standing waves, something we discussed a bit in class. But here we have the specification points that are being covered as well. So let's scroll down to the correct section of explaining everything. Right, here we go. So in this place below, complete the following tasks. A wave labelled with key features, so that's wavelength, frequency and amplitude. Include the wave equation, how to calculate the period or time period. Compare and contrast longitudinal and transverse, and compare and contrast standing and progressive waves. Okay, let's go to the first one. So we've got a wave that looks like this. Okay, straightforward, it hasn't shown up very well. Yeah, it's much better. Okay, so the wavelength is from two identical points on a wave like so. Okay, so any of those is the wavelength. Now, the frequency can't be shown on here, but we know the frequency is the number of waves per second. Number of waves per second. Okay, it says the amplitude, so remember the amplitude is the height of the wave from the middle. Pretty straightforward to start off with. The wave equation says V is equal to F times lambda. Remember, just going back to amplitude for a second, remember it is always from the middle, not top to bottom, always from the middle. Middle to the top or middle to the bottom. V equals F lambda is the wave equation. Remember time period is 1 over frequency. It's nice and straightforward. Right, compare and contrast longitudinal and transverse waves. So remember transverse waves, longitudinal waves, let's go with first. Areas of compression and then areas of rarefaction where they're spread apart. So where you have the areas of compression, so sorry, ignore this bit that I've scribbled out over here, where you pick the two parts of compression are equal, that's a wavelength, so same part on both of these, so from there to there would also be a wavelength. So that's called area of compression, and rarefaction from there to there, rarefaction from there to there. There and there are areas of rarefaction. Here is an area of compression, here is also an area of compression. So rarefaction is there, there, and there, compression is there and there. It's a longitudinal wave. Transverse waves are like the waves you drew above. Okay, so that's pretty straightforward. So remember, in this, particle motion is parallel to wave motion, to the wave if it went from left to right. Particle motion will also be from left to right. Over here, particle motion is up and down, while the wave motion is going from left to right. Okay, so it's perpendicular to wave motion. So particle motion is perpendicular to wave motion. Perpendicular is parallel to wave motion. So this is something like that's known as a mechanical wave. Okay, electromagnetic waves are these. Sound waves are longitudinal. Electromagnetic waves and light and all those are transverse. They're the main waves they talk about. Right. Final bit. Compare and contrast standing and progressive waves. Okay, so standing wave is generally set up by having a pipe of some sort or reflecting off a boundary of some sort. So you've got points like this where every single point on this point is going down and every single point on this point is going up. And half a cycle later this point will be on top and this whole point will be at the bottom. Okay, in a progressive wave that wave will be moving. So standing wave is interfering with its own reflection, or two waves are interfering which is causing this to be set up. In a progressive wave, the wave are moving. So if that moves, the wave is moving to the left. If I pick the same point over here, that's on its way down. Okay, it's going to go down to the bottom, then it's going to be on its way up after that, and then it'll be on its way down again. So if the wave moved in that direction, that's the same idea as a particle moving in this direction, but along the line. So travelling waves are waves that are moving. While the standing waves are waves that are essentially standing still and just flipping. So I think I've showed it with my finger before like this, where you've got a curved thing like that and it flips over. It's quite hard to show. I've done it with my hands before, I know in class. So the idea it flips from that position to that position. Okay, it's a standing wave. Or a progressive wave, the wave is there and it moves from left to right, or the particle goes in the opposite direction. So it's going to go down, it's going to go up. So if I start over here, that particle will go up and then go down again in terms of progressive wave. Brilliant. So it's the difference between progressive and standing waves. Let's get stuck into these questions then. So, Oh, there we go, just went past them. So the first one, source of light emits a train of waves lasting 0.04 microseconds. So that's the time for these waves. The light has a wavelength of 600 nanometers, and the speed of light is that how many complete waves are sent out. Well, if we know the distance that this thing has travelled, this train has travelled, we can figure out how many wavelengths have been sent out, and therefore the complete numbers of waves. Okay, so speed is equal to distance over time. Distance is therefore speed times time. So we've got 3 times 10 to the 8 times by 0.04 times 10 to the minus 6. Okay, it's minus 6 because micro. 3 exp8 times 0.04 exp minus 6. So it's 12 meters essentially. I think I missed something out there. Let's have a check. Divided by 600 exp minus 9. Okay, so we've got 20 and times 10 to 10. Look, just 1, 2, 4, 5, 6, 7. 7, sorry. 2 times 10 to minus 7. So it's A. The first one is A. So we'll double check that in a second. Electromagnetic waves are produced by oscillating charges. Sound waves are produced by oscillating tuning forks. How are the waves similar? So, one's electromagnetic, transverse, one's sound, longitudinal. Can't be the top two then. They're both have the same frequency as the respective sources. Correct, that is true. So, however quickly the tuning fork is vibrating, that's how quickly the sound, that's the same frequency sound, and same idea as electromagnetic waves. So, if the electron is going up and down, it will release a wave of the same frequency as that. They both don't require medium travel through, electromagnetic waves don't. Okay, so it's A and C. Let's double check. A and C, brilliant. Okay. So suggested that tigers use infrasound, low frequency sounds inaudible to humans to keep rivals away from their territory and to attract mates. Sound is a longitudinal wave described as sound travels through the air. Right, so it travels as compressions and rarefactions. So areas of compression and area of rarefaction. Okay, the wave motion is parallel to particle motion. Okay, so the particles vibrate parallel to the wave motion. State what is meant by frequency, so number of waves passing a single point per second, or number of waves per second. The frequency range of sound produced by tigers extends down to 18 Hz. Calculate the wavelength in air for the sounds of this frequency. So you've got the speed there. So essentially just using speed is equal to frequency times wavelength. So they want the wavelength, so therefore you do speed over frequency. So it's 330 divided by 18. Okay, so yeah, it's about 18 again, 18.3 meters. Okay, so that's right, long wavelengths. It could be a low frequency, so it'll be a long wavelength. Let's have a look. 18.3 meters, number of oscillations or number of waves per second or per unit time. Particles oscillate or vibrate parallel to wave motion. There you go for the second mark. And compressions and rarefactions are formed areas of high pressure, low pressure. Brilliant, nice and straightforward. Right, 14. Now I know this question causes some people some issues, so let's go through it carefully. You want to figure out the wavelength, so you need to draw a sine curve in here and figure out the wavelength. So if you look at that, it's going from about 1. Actually, let's take this point here and this point here. They're almost identical. Yeah, almost. It'll be about over here actually. Then just creeping onto 13. So about 13 meters. Okay, so if we take this side of this, where it next reaches there is about 13 centimeters. So about 13 centimeters is the wavelength. Next, so find the value of the amplitude. Okay, well, to do that we need to use this as a scale. So you need to use your ruler, compare it to this, and then figure out the height of this and compare it to that. So you measure the height, so that's the difference between the lowest point, which is this one here, and that one. So measure the height from here to here. Okay, half it, and then take that length, compare it to this ruler here, which will tell you what the amplitude is. So say it ended up being this big for your amplitude. Okay, it's kind of hard to show on this, okay, but say it ended up being this big for your amplitude. You then take that, you turn it on its side, and you see how much that is over here, okay, and then compare it to the value of amplitude you actually end up getting. Sorry. Right, so the machine is operated so that every rod along the wave moves up and down for a complete cycle every 2 seconds. So the time period is 2 seconds. The frequency is therefore going to be 1 over 2 seconds. That's 0.5 hertz. What is meant by transverse wave? Spoken about it before. The particles oscillate perpendicular to wave motion. Discuss whether this machine will be helpful in illustrating how a sound wave travels. Well, no, because in a sound wave, remember, it's parallel to wave motion, and this only shows perpendicular to wave motion. Energy, wave transition, wave propagation, parallel to wave. Sorry, let me say this again. That diagram, that machine only shows wave motion parallel to particle motion, perpendicular to particle motion, while in sound wave it'll end up being parallel to particle motion. Lots of P's in that sentence. Okay, so the machine shows perpendicular to wave motion, while sound is parallel to wave motion, so that can't be demonstrated by that machine. Okay, so let's get the right ones up. So the first one over here, description of sound. Oh no, we've been through that one already. It's this one over here. So they're saying about 13.9. Okay, so that's 13.9 divided by 0.5, so it's still about 30.4. So yes, that would be acceptable range to choose from. So that's great. So again, that's what we spoke about. Amplitude is half of the peak to peak. So there we go, 0.5 hertz, and oscillations or disturbance at a right angle, and sound needs is right angle. That's what transverse means. This is oscillation, not in direction of wave. So that's exactly what we spoke about. Remember, propagation just means movement. So propagation is the same as wave motion. So sound is not transverse. So the oscillations are going to be in compressions or rarefactions, like we said. So the model is not useful. Brilliant. Okay, so that's that key section for this bit over for the question we've just answered. Right, 15. Nearly there. Right, okay, so which letter indicates the wavelength of sound? So the wavelength there, the only one that shows that is D. C is showing double the amplitude. B is not showing the wavelength. A is showing the amplitude. So sound travels at 330 meters per second. Calculate the period of the wave. Well, they've got over here the wavelength, so therefore we can figure out the frequency, and then from the frequency figure out the time period. So if we look back at our equation from before, frequency, if we rearrange, is going to be V over lambda, so that's 330 divided by 0.66 meters. 330 divided by 0.66, so that's 500. Okay, so that's our frequency. We do 1 divided by 500, tells us our time period, so that's 0.002 seconds. Okay, so we'll double check that right in a second once we've had a look at the next question. So we've got a progressive wave, so that's a moving wave, it's a travelling wave, okay? And they differ by pi over 4. Right, let's get these values right in our head. Let me just find a blank space on this to go through this. Okay, so 2 pi equals 360 equals lambda. So pi is equal to 180 is equal to lambda over 2. So lambda over 2 is equal to 90, which is equal to pi over 2 is equal to 90, which is lambda over 4. So pi over 4 is therefore equal to 45 degrees, which is lambda over 8. So it's an eighth of a wavelength out is what we're talking about. The distance between them is 0.5 meters. Okay, the frequency is 10. Calculate the speed. Okay, so if you want speed and you have the frequency, you need the wavelength. Okay, so we want the speed. Okay, but when it's frequency times our wavelength. Okay, they're out by a set amount. Okay, we're saying that an eighth of a wavelength is 0.5 meters. So therefore the wavelength will be 0.5 times by 8, which is 4. Okay, so I don't know why I went for the calculator there. I've picked that habit up from you guys. That's a bad habit. Okay, so 4 meters is my wavelength. Again, that's another habit I picked up. I should write wavelength is equal to 4 meters like that. Okay, so wavelength is 4 meters. Frequency is 10, so it's 40. So that makes that D. Okay, which of the following statements about a standing wave is true? So the particles between adjacent nodes all have the same amplitude. Well, we know that's not correct. They all have different amplitudes. Particles undergo no disturbance at an antinode. Antinodes have maximum displacement, a maximum amplitude. Antinode amplitude. Okay, so nodes are no displacement. Antinodes are maximum displacement. Particles immediately either side of a node are moving in opposite directions. Let's have a look at that. So let's get a standing wave diagram before. Here's a node. Particles moving in opposite directions, either side of it. Brilliant. So that's going down, that's going up. Perfect. That sounds right so far. Particles between adjacent nodes are out of phase with each other. Well, no, they're all in phase because they're all going together at the same rate, up and down. So they're all in phase with each other. So that makes that C. Let's double check this. Okay, so D and then C. Yep. We've got D over here and we've got 0.02. There's that one over there. Okay. So now on to 18, let's have a look. Okay, 18. Oh, right, so we've done this question before in class. It's a nice question to get. A lot of people trip up on it. Again, we've got the idea of a wave moving on a rope. Okay, the wave is traveling. It's a traveling wave, it's a progressive wave. Instant L is at maximum displacement and M has 0 displacement. Which row correctly describes the motion of L and M in the next half cycle of wave? Okay, so remember, if the wave is going this way, the particle is going this way along the wave because it's a travelling wave. So M's next going to go down, then up during the next half cycle. So it's going to fall and then rise. So automatically we're going with B and D. Okay, L is going to rise, and if you think about the next part of this wave up here, it's going to rise again. So that makes that D. Sorry, no, not D, B. Okay, it rises, and M just rises and falls. Okay, so we'll double check that for 18. We'll double check 18 is D. And then we've got question 19 to finish off. Yep, B, brilliant. Okay, so 19A, let's have a look. Right, so we've got a standing wave set up on it, and we want to know the wavelength of it. Okay, the frequency is at 60 Hertz. Okay, so guessing they might talk about the speed at some point. But let's have a look at the wavelength. So how many waves have we actually got on here? We've got 1.5 waves, and that's 1.5 meters. So therefore, one wave must be 1 meter. Straightforward. First question is just 1 meter. So 1 meter for that wavelength. Next, the frequency of the vibrator is altered into a standing wave. There's 2 more nodes. Okay, so let's draw this out now. So we've got 2 more nodes. So we've got one node there, one node there, another node there, another node there. Okay, so there's one more node there and one more node there. So we had 1, 2, 3, 4 to begin with. Let's double check that. 1, 2, 3, 4. Okay, and now we've added 2 more nodes. Okay, so that's now what we've got. The length is still the same. So length is still 1.5 meters, but our wavelength is now going to be different. How many waves have we got? We've got 1, we've got 2.5. We've got 2.5 waves for 1.5 meters. So our wavelength, so essentially what we're saying is the wavelength is equal to L divided by 2.5. Okay, so the wavelength is L divided by 2.5 is what we're saying. So one wavelength is L divided by 2.5 because there's 2.5 wavelengths in there. So 1.5 divided by 2.5 gives us 0.6. So our new wavelength is 0.6 meters. Then we'll figure out the frequency. Well, we don't actually have the speed, but we can figure it out from before. So that's our wavelength. But our speed is a question mark. Well, it's going to be the same speed as before because it's the same material. So why don't we just do it with the previous calculation of 60 times by 1? Okay, because 60 is the frequency and 1 was the previous wavelength. So that ends up with 60 meters per second. So the speed must still be the same. So now our new speed is still 60 meters per second. Our new frequency, well, that's going to be speed over wavelength. So that's 60 divided by 0.6. which equals 10. Okay, so that should be 10 hertz for that one. And that makes sense. Hold on. I'm not sure about that now. I should double check in case I made a mistake. Wave speed equals frequency times wavelength. Oh, wave speed equals... No, I've done that correctly there. I've probably made a mistake somewhere. Let's have a little check. Oops, daisy. Oh, I think I've typed something in wrong to my calculator. It might be 0.06 from the wavelength. Let's have a look. Yeah, it should have been 0.06, I think. Let's just see where I went wrong with that. So 1.5 divided by 2.5 is equal to, no, it's 0.6 times by 60 equals, no, that's not right. Apologies, it did say 100. I'm just being stupid. The sum that I did was correct. I don't know what I did wrong there. I'll probably put probably missed a decimal place out. So 60 divided by 0.6 is 100, which it should be. I thought I did that right. So always double check your calculations, guys. Right. That is the end of the video. Some ends on a nice funny note there. End of the video of task 3 on the Waves ISP. So we've got 2 more tasks left after this. Right, so thank you very much for listening, guys.